Welcome back to Sustainability and Engineering. I'm Engineer Shaaz Hussain Syed, and this is week 2 of our CPD session. First of all, thank you to everyone who watched and engaged with week 1. In the previous session, we spoke about MEP scope, what it includes and what it excludes, and why misunderstanding scope is one of the biggest reasons MEP projects struggle. Today's session is a direct continuation of that discussion. Because understanding scope is only half the story. The other half, and the more dangerous half, is understanding your role within that scope. Today's topic sounds very simple in words, but is extremely complex in real engineering practice. Now, what is the role of an MEP engineer? Let me be honest. Many engineers work 5 years, work 10 years, even work for 15 years. Yet, when asked a basic question, they hesitate. They struggle to clearly explain what is exactly my role in the project, where does my responsibility start and end, where does my liability stops. And this confusion has real consequences. From experience, lack of full clarity leads to project delays, engineer-contractor conflicts, authority rejections, endless variation in claims, and engineers being blamed unfairly. In week 1, I said, if scope is not clear, responsibility will be forced on you. Today, I'll add, if your role is not clear, liability will find you. So this session is especially important for young engineers moving from design to site, engineers entering supervision roles, engineers working in design and build projects. By the end of today, you should confidently be able to say, this is my role, this is my responsibility, and there is where my liability ends. So let's begin. Now let's talk about why role clarity is critical. Before we talk about design or supervision, let me ask you a simple question. When something fails on site, who is responsible? Most people answer quickly, the contractor, the consultant, the client. On paper, these answers sound logical. But in reality, responsibility often lands on the engineer who crossed his role boundaries. Here is the key truth. As engineers, we are not protected by intentions. We are protected by documentation. You are protected by your contract, your defined scope, approved drawings, written records. As long as you stay within these boundaries, you are professionally protected. But the moment you give verbal instructions, the moment you redesign casually on site, the moment you approve work outside your scope, you lose that protection. You stop acting as a protected engineer and start acting as an individual, taking liability. And remember this reality. When something works, nobody remembers who helped. When something fails, everybody remembers who spoke. This is why role clarity is not about ego or avoiding responsibility. It's about professional survival. Once you understand this, design becomes safer, supervision becomes stronger, design and build decisions become smarter, careers become more stable. Now let's define each role clearly. Now let's understand the role of an MEP engineer in design projects. What is a design project? A design project is the most common starting point for engineer. In a design project, the consultant is appointed only to design, not to build, not to supervise, not to control site works. Responsibility is very specific. Design MEP systems that work, comply and last. In a pure design role, no construction responsibility, there is no site supervision, and there is no execution control. Your authority exists on paper, and that is not a weakness, it's a protection. Your deliverables are design drawings, calculations, specifications, authority compliant submissions. Once these are approved, your role ends. What happens on the site belongs to others. Now let's talk about primary responsibilities of a design MEP engineer. And I want you to remember one key point from the beginning. Designing is not drafting. Drafting is drawing what you're told. Designing is deciding what the building actually needs. So where does design start? It starts with a concept design. This is where engineering really begins. At concept stage, you decide the basic direction of the building systems. For example, do we need a centralized system or a decentralized system? Do we go for the chill water, DX, VRF? What is suitable for this project? What is the level of redundancy required? Do we need backup pumps? Do we need dual power supplies? These are not small choices, because concept design directly affect energy, cost, maintenance, and long-term performance of the systems. After concept comes schematic layouts. This is where many engineers think it's just lines on a plan, but it is not. Here you are planning the reality of the building, where equipment will sit, how services will route, where shafts will go, how much space you need, and how MEP will coexist with architecture. This is decided in this stage of the project. Good schematics prevent the most expensive problems on the project. Site clashes and redesign during construction are avoided in this phase. Now next comes the detailed design. This is where coordination becomes non-negotiable. Now you must align your MEP design with architecture, with structure, with ceiling heights, with plant room constraints, with access for maintenance. Because a drawing that looks perfect but clashes with the structure is not engineering. It becomes rework, becomes delay, and it gives you cost variations. Then we move into the backbone of the design, that is load calculations. What does load calculations have? As an MEP, load calculations usually include HVAC loads, electrical loads, water demand loads, drainage and pump sizing. If these calculations are wrong, everything collapses after that. Wrong calculations lead to oversizing, energy wastage, comfort complaints, unstable operation, and higher life cycle costs. After calculation comes equipment selection and schedules. Here's where I want to be very clear. Equipment selection is not about choosing the cheapest product, and it's not about choosing the brand you're familiar with. A design engineer selects equipment that meets performance, and equipment is efficient, an equipment which is maintainable, and an equipment which has local support, and an equipment which can realistically be serviced after handover. Now finally we come to the authority submissions. Because even a technically good design can fail if it doesn't meet the authority requirements. A design that cannot get approval is still a failed design. So a good design engineer continuously asks simple but powerful questions. Is the system really required? Will it work after handover? Is it safe? Is it compliant? Can the FM team maintain it? And that's why I say again, designing is engineering thinking, not drafting. Now let's talk about something that is not written in any code or standard, the mindset of a design engineer. A good design engineer does not think only about today's drawing or today's deadline. He thinks beyond handover. Unfortunately, many engineers, especially early in their careers, fall into a very common trap. They ask, how fast can I finish this drawing? Speed becomes the goal, not quality, not performance. But experienced design engineers think differently. They ask, will the system actually work in real operation? When the building is occupied, will it perform the way it was intended? Can the FM team maintain it without constant breakdowns, complaints, and callouts? Is the system energy efficient? Not just on paper, but throughout its operating life? And very importantly, will this design pass authority approval smoothly, without endless comments and resubmission? Because once a building is handed over, drawings no longer matter. What matter is comfort, reliability, energy consumption, maintenance cost, and user satisfaction. This is why design mistakes are so dangerous. On paper, a mistake may look very small. It could be just a line on the drawing, a wrong assumption in calculation, or a piece of equipment selected in hurry. But on site and after handover, that small mistake becomes very, very expensive. It turns into rework, it may turn into complaints, it may turn into high operating costs. Sometimes it turns into complete system failure. And by then, fixing it is no longer simple or cheap. A strong design engineer understands this. He slows down where it matters. He takes responsibility for decisions that may not show impact immediately, but will define the building's performance for years. That is mindset shift every design engineer must make. Designing is not about finishing drawings. Design is about owning long-term consequences. Now, this is the point where many engineers, even very good engineers, unknowingly make mistakes. Not because they lack knowledge, but because they are trying to help. And this is where we must be very clear. A design engineer is not responsible for construction methodology. A design engineer is not responsible for installation sequence. A design engineer is not responsible for contractor manpower or workmanship qualities. These responsibilities belong to others, and they are clearly defined in the most project contracts. Once your design drawings are issued, reviewed, and approved, something very important happens. Responsibility shifts. At this stage, the contractor owns construction and the supervision consultant controls execution. This separation is not about avoiding responsibility. It's about placing responsibility where it legally and professionally belongs. The danger starts when a design engineer crosses this boundary. For example, giving instruction directly to a site staff, suggesting construction methods informally, or approving changes on site without going through proper authority and documentation. Even if the intention is good, the consequences can be serious. Because the moment a design engineer interferes on site without authority, liability increases immediately. At this point, you are no longer acting only as a designer, you are influencing execution. And when something goes wrong, the question will not be who was responsible by contract. It will be who told them to do this. Strong professional engineers understand the risk. They know when to step back, they know when to document instead of speaking, and they know that respecting boundaries is not weakness. It is professional protection. You protect the project, you protect the client, and most importantly, you protect yourself. When we talk about sustainability, many people immediately think about ratings, certification, or green labels. But in reality, sustainability starts much earlier. Sustainability starts at design stage. As a design engineer, every decision we make has a direct impact on how much energy a building will consume over its entire life. Correct equipment sizing is one of the simplest but most powerful examples. When systems are sized properly, energy consumption drops, performance improves, and equipment lasts longer. When systems are oversized, energy is wasted every single day. Proper zoning is another critical design decision. Good zoning ensures that spaces are conditioned only when required, and that different usage patterns are respected. Poor zoning leads to unnecessary cooling or heating and pure energy wastage. Then there is routing. Efficient routing of ducts, pipes, and services reduce material usage, lower pressure losses, and improve system efficiency. Shorter, smarter routes means less material, less energy, and less embodied carbon. Plant and equipment selection also plays a huge role. Smart plant selection is not about choosing the biggest or most familiar systems. It is about selecting systems that are efficient, reliable, maintainable, and suitable for project's real needs. On the other hand, Careless design creates serious long-term problems. It creates buildings that consumes excessive energy, that have high operation and maintenance cost, and that have poor indoor comfort for occupants. And these problems do not disappear after handover. They stay with the building for decades. That is why sustainability is not something we fix later at site. Sustainability is designed or it is lost. A good design engineer understands this and treats sustainability not as an add-on, but as a natural outcome of good engineering decisions. Now let us move into the part 2, supervision projects, because this is where many engineers experience the biggest shift in their role. In a supervision project, two very important things are already decided. First, the design is already completed and approved. Second, the contractor is already appointed. So your job here is very different from a design role. You are not being hired to redesign systems. You are not being hired to execute the work. Your role is simple in definition, but very powerful in impact. To monitor and control construction. As a supervision MEP engineer, your responsibility stands on 3 core pillars. The first pillar is compliance. You must ensure that all work on site follow the approved drawings, specifications, and applicable codes without exception. The second pillar is quality. Your role is to ensure that installations are done properly, safely, and in line with the engineering standards, not just completed quickly. The third pillar is documentation. This is what protects the project, the client, and you as an engineer. If something is inspected, commented on, accepted, or rejected, it must be documented always. And this is where I want to be very clear. As a supervision engineer, you are not design engineer, you are not the designer, and you are not the contractor. You are the technical referee. Just like a referee in the match, you do not play the game, but you ensure the game is played according to the rules. Your authority does not come from shouting on site. It does not come from giving quick verbal instructions. It comes from approved drawings, written comments, inspection reports, and a proper record. Once you understand this role clearly, supervision becomes structured, professional, and defensible. And most importantly, it protects you. Now let us talk about authority, because this is where many supervision engineers misunderstand their real power. Your authority as a supervision engineer does not come from redesigning the system. It does not come from casually approving changes on site, and it definitely does not come from giving verbal instructions. In fact, the moment you redesign something on site, or approve deviations casually, or instruct verbally, you start losing authority instead of gaining it. So where does your real power come from? Your real power lies in documentation. It lies in clear written technical comments, strict references to approved drawings, proper site inspection reports, and formal records like work inspection requests and material inspection requests. These documents are not paperwork, they are legal protection. Let me say this very clearly, because this is one of the most important lessons in supervision. If it is not written or documented, it does not exist. You may explain something perfectly on site. Everyone may nod and agree, but the moment there is a failure, delay, or dispute, nobody will remember the conversation. What they will ask is, what was approved in writing? What was recorded in inspection reports? What was accepted or rejected formally? A strong supervision engineer understands this and stays disciplined. Instead of reacting verbally, he documents. Instead of arguing, he records. Instead of redesigning, he refers to the approved drawings. That is how you control construction professionally: calm, structured, and defensible. And that is what real authority looks like in supervision. Now let's talk about what supervision actually looks like day to day, because this is where many engineers misunderstand the role. Supervision work is not random. It is structured, repetitive, and disciplined. A supervision MEP engineer does not just walk around site or attend meetings. He follows a clear technical process. One of your key responsibility is shop drawing review. This is where the contractor translates design intent into buildable details. Your job is to verify that these drawings follow the approved design, respect the coordination, and do not introduce hidden deviations. Next are material submittals. Here you check that the material proposed match the approved specifications, meet the project standards, and are suitable for intended application. Approving the wrong material once can create long-term operational problems. Then comes site inspection. This is where supervision becomes real. You physically verify that installation match approved drawings and are accessible and are installed correctly before they are concealed in false ceiling, of course. Closely linked to this are installation checks. Once work is closed, mistakes become expensive and difficult to correct. Your inspection at the right time prevents future failures. You also participate in coordination meetings. These ensure that MEP works align with the architectural and structural progress and that conflicts are resolved early. Finally, there is testing and commissioning. This is where systems prove that they work as designed. You witness tests, review results, and ensure deficiencies are properly closed. Across all these activities, your responsibility remains constant. You must ensure the work on site matches the approved drawings. You must ensure the materials installed match with what was approved, and you must also ensure that the installation meets the required standards. And you achieve this through documentation, because in supervision, one rule always applies. What is documented is what exists. If it is not recorded, it will not protect you. A disciplined supervision engineer documents consistently, and that is what keeps the project and the engineer safe. Now let's talk about common supervision mistakes, because almost every engineer makes at least one of these earlier in their career. The first and the most dangerous mistake is redesigning at site. A supervision engineer may see an issue and try to fix it quickly by changing the detail during execution. The intention may be good, but the impact is very serious. The moment you redesign at site, you step outside your role and take on design liability. The second common mistake is verbal approvals. Phrases like, "Okay, proceed for now." Phrases like, "We'll just sort it out later." Phrases like, "It's just fine, just continue." These sentences feel harmless at the moment, but when something fails, there is no record and no protection for it. Another mistake is ignoring small deviations. It's very easy to think it's just a small offset or it won't make much of a difference. But small deviations do not stay small. They accumulate, and when systems are tested or occupied, they turn into performance problems, complaints, and failures. And finally comes poor documentation. Inspections, if not recorded, comments not issued, approvals not traceable. From a contractual and professional point of view, if it is not documented, it never happened. And this leads to one simple truth in supervision. Small deviations today become major failures tomorrow. A strong supervision engineer does not redesign. He does not approve verbally. He does not ignore deviations. He documents, escalates properly, and protects the project through discipline. That is the difference between reactive supervision and professional supervision. When we talk about sustainability, most people immediately think about design. But there is an important reality we must accept. Sustainability can be lost at site. No matter how good a design is, if supervision is weak, the sustainability intent of the project disappears. Let me give you some very simple real examples. Poor insulation may not look like a big issue during installation, but even small gaps or damaged insulation results in continuous energy loss every single of the day of the building. Poor balancing is another common problem. If air and water systems are not balanced correctly, some spaces become uncomfortable, others are overserved, and energy consumption increases drastically, and which is unnecessary. Then there is a bad installation. Incorrect slopes, loose connections, improper supports, or rushed workmanship may not fail immediately, but over the time, they lead to inefficiency, breakdowns, and premature system failure. And all of this directly affects sustainability. This is the key point every engineer must understand. Buildings do not operate based on drawings. They operate based on what is installed. A project can have highly sustainable design on paper and still perform poorly in reality if supervision is weak. That is why supervision engineers play a critical role in sustainability. By enforcing a proper installation, by enforcing approved material, and by enforcing correct testing and commissioning. You're not just protecting quality, you're protecting the building's long-term energy performance, comfort, and environmental impact. Good supervision ensures that sustainability is not just designed, but actually delivered. Now let us move to part 3, design and build projects, which are often the most challenging environment for an MEP engineer. In design and build setup, one fundamental thing changes. The contractor is responsible for both design and construction. That single shift makes the role of MEP engineer far more complex. In traditional projects, design and construction are separated. In design and build, they happen together, and often at the same time. This means MEP engineer can no longer think in a single role. You must think like a designer, ensuring the system is technically sound and compliant. You must think like a supervisor, ensuring the design can actually be built at site. You must think like a cost controller, understanding how every decision affects the project budget. You must also think like a coordinator, aligning design with construction sequences and constraints. And last, you must also think like an ultimate leader, guiding decisions and managing risks. In design and build, design decisions do not stay on paper. Every decision you make affects what happens at site, how much the project costs, and whether authorities approve it or reject it. And these impacts happen immediately. There is very little time to fix it later. There is very little room for trial and error. That is why design and build is not just about technical knowledge. It demands judgment, experience, and responsibility. A strong design and build engineer understands that he is not just drawing systems. He is shaping how the project will be built, approved, and operated. And this is what makes design and build both powerful and risky. Handled correctly, it produces efficient, optimized projects. Handled poorly, it creates delays, disputes, and long-term failures. This is why the role of MEP engineer in design and build is the most demanding and the most important. Now that we understand what design and build really means, let us talk about responsibility, because this is where the pressure truly begins. In design and build projects, the MEP engineer is not just finalizing drawings. You are shaping how the project will be built, approved, and operated. One of your first responsibility is to develop the design from concept. In many design and build projects, you do not start with a fully functional, detailed design. You start with the performance requirements, budgets, and timelines. Your job is to translate all of that into a complete buildable MEP design. At the same time, authority compliances becomes very critical. In design and build, approvals often run in parallel with construction. This means your design must anticipate authority requirements from the very beginning. A delay in approval can stop the site work immediately. Then there is cost optimization. Every design decision in design and build has a direct cost impact. Selecting a system, changing a route, or increasing capacity immediately affects the budget. A strong design and build engineer designs with commercial awareness, optimizing cost without compromising performance or safety. Another key responsibility is execution coordination. Your design must be constructible.
That means coordinating closely with site teams, procurement and planning. A design that looks perfect on paper but cannot be built efficiently will create delays and disputes. And finally, there is solving design side conflicts. In design and build, conflicts are inevitable. The difference between a weak and a strong engineer is how these conflicts are resolved. Quickly, technically, and with the proper documentation. Throughout all of this, one principle must guide every decision. Balance. You must constantly balance performance. That means the system must work reliably. You must constantly balance the cost. That means the project must remain financially viable. And you must also constantly balance the constructability. That means the system must be buildable on site. Lean too much towards one and the project suffers. This balancing act in which is what defines a competent design and build engineer, and it is what prepares engineers for leadership roles. Design and build projects can be very rewarding, but they are also extremely unforgiving, especially for engineers who are not prepared for the responsibility. Let me explain why. One of the biggest risks in design and build is over-design. When systems are oversized, overspecified, or made unnecessarily complex, the budget is hit immediately. Costs rise quickly, and once procurement starts, these costs are very difficult to reverse. On the other side, under-design is just as dangerous. A system may look acceptable on paper, but if it cannot meet the real operational demands, performance suffers. That leads to user complaints, retrofit work, and long-term dissatisfaction. Then there is poor coordination. In design and build, design and construction happen in parallel. If coordination is weak, drawings change late, site work stops, timelines slip, and disputes begin. This is why design and build does not allow shortcuts. You cannot blindly copy drawings from previous projects and assume they will work. Every project has different constraints, approvals, and operational requirements. You also cannot blindly trust vendors. Vendors promote products, but it is not their responsibility, but it is your responsibility to verify performance, compliance, and long-term sustainability and suitability. And this is the key reality every design and build engineer must accept. Every single decision you make has consequences. Each decision affects costs, authority, approvals, and professional liability of the engineer. Weak engineers focus only on finishing drawings and the project. Strong engineers think through the consequences. And that is why design and build quickly exposes the difference between engineers who follow the instructions and engineers who truly lead the projects. Design and build projects demand a very different level of maturity from an engineer. In this environment, technical knowledge alone is not enough. The first requirement is strong engineering fundamentals. In design and build, you often do not have the luxury of long review cycles. You must understand how systems actually work, why certain solutions are suitable, and what will fail if something is done incorrectly. Next is site experience. If you have ever seen how systems are installed, tested, and commissioned, your design decisions will be disconnected from reality. Site experiences help you design systems that can actually be built, not just drawn. Another critical skill is authority knowledge. In design and build projects, approvals often run alongside construction. You must understand authority requirements, approval workflows, and common rejection points. An engineer who does not understand this becomes a bottleneck to the entire project. Then comes commercial awareness. Every design decision in design and build has a cost implication. A stronger engineer understands where money is being spent, where value engineering is possible, and where cost cutting will create long-term problems. This is not about designing cheaply, it is about designing smartly. And finally, there is decision-making confidence. Indecision is more dangerous than slow progress. You will often have to make decisions with complete information under time pressure and with multiple risks involved. A strong design and build engineer makes those decisions, documents them properly, and stands by them. And this is the key transformation. This is where engineers stop being draftsmen and start becoming leaders. This is the stage where engineers take ownership, manage risks, and shape projects, not just drawings. Design and build projects give MEP engineers a unique level of influence when it comes to sustainability. In this setup, sustainability is not just a concept written in a report. It is shaped by daily engineering decisions. As a design and build engineer, the systems you design are systems that will be built. That means your choices directly affect the building's environmental footprint. One of the biggest opportunities in design and build is system optimization. When systems are optimized, neither oversized nor underperforming, energy demand is reduced, equipment life is extended, and embodied carbon is minimized. Layout decisions also play a major role. Efficient routing of ducts, pipes, and services reduce material usage, lower pressure losses, and improves overall system efficiency. Less material and less energy during operation means better sustainability outcomes. Then there is smart equipment and smart system selections. In design and build, you are often involved in selecting systems based on performance, availability, and cost. Choosing reliable, efficient equipment reduces maintenance, extends life cycle of performance, and lowers long-term operating costs. This is where sustainability goes beyond energy efficiency. It becomes about life cycle thinking, from installation to operation, maintenance, and eventual replacement. And this leads to an important conclusion. Design and build engineers do not deliver projects, they shape sustainable outcomes. The decisions you make today will define how the building performs for decades. That is why design and build carries both responsibility and opportunity. Handled correctly, it produces projects that are efficient, resilient, and truly sustainable. Before we close, there is one important issue we need to address openly. That is blame culture. Blame culture does not exist because engineers are careless. It exists because rules are not clearly understood or respected. On many projects, when something goes wrong, the first reaction is not to fix the problem. The first reaction is to assign the blame. You will see designers blaming contractors for poor execution, supervision engineers blaming designers for unclear drawings, and design and build engineers blaming clients for changing requirements. And while there may be a partial truth in all of these, blaming does not improve projects. What actually creates this situation is role confusion. When roles overlap, responsibility becomes unclear. When responsibilities is unclear, everyone tries to protect themselves. And that is when communication breaks down and conflict begins. A professional engineer approaches this very differently. He knows exactly what he's responsible for. He knows what he can influence and what is outside his role. He does not absorb responsibility that does not belong to him, but he also does not avoid responsibility that does. This clarity changes behavior. Instead of blaming, the focus shifts to proper documentation, clear communication, correct escalation, and informed decision making. And this is why role clarity is very powerful. It reduces conflicts, it protects careers, and it creates healthier, more successful projects. A professional engineer always operates with one simple mindset. This is my responsibility and that is not. And that mindset makes all the difference. Let us now bring everything together. Throughout today's session, we have spoken about rules, not job titles, not designations, but real responsibilities on real projects. At its core, the message is very simple. Design engineers create systems. They shape how a building will function, perform, and sustain itself over time. Supervision engineers protect systems. They ensure that what was designed is installed correctly, safely, and in full compliance with the standards. Design and build engineer optimize systems. They balance performance, cost, constructability, approvals, and long term value. These roles are different, but they are equally important. Problems begin when these roles are misunderstood, mixed, or ignored. But when roles are very clear, everything changes. Projects become more structured, conflicts reduce because responsibility is clearly defined. Sustainability improves because decisions are deliberate and well thought out. And careers grow because engineers operate with confidence, clarity, and professionalism. This is the key point I want you to remember. Role clarity does not limit you, it protects you. It protects you from unfair blame. It protects you from unintended liability, and it allows you to make better decisions without fear. As you go back to your projects, I want you to carry these 3 simple principles with you. Know your role, respect your boundaries, document your decisions. If you do this consistently, success will follow. Not just for the project, but for your career as well. With this, let's end this session. I'm your host, Engineer Shaaz Hussain Syed. Thank you everyone for joining this CPD session, and I look forward to seeing you in the next session. Goodbye.